Geometry lesson 2-3. Continuing with the discussion about conditional statements and biconditional statements, we actually have some symbols that we can use to abbreviate or symbolically represent the converse, the inverse, contrapositives, conditional statements, biconditional statements. So to start with, we'll look at conditional statement. We still have the hypothesis and the conclusion. That hasn't changed. We'll refer to the hypothesis as P and the conclusion as Q. So we would pronounce this symbol. This is the symbol for any conditional statement, hypothesis, then Q. It would be pronounced if P, then Q. So it's still in if-then form. If the hypothesis happens, then Q will happen. So I like to think of this as mind your P's and Q's, even though that's not necessarily the origination of that saying. But this is mind your P's and Q's, if P, then Q. Starting at P with an arrow going to Q, as if you had P happen, as a result, Q would happen. Now, how does this same symbols kind of apply when we're dealing with a biconditional statement? Remember, biconditional statements have to work both forward and backward. So the symbol now says, and it has an arrow going back and forth, because it has to work both forward and backward. If P, then Q, and if Q, then P. Notice that's forward and backward. If the hypothesis, then the conclusion, and if the conclusion, then the hypothesis. In order for it to be a true biconditional statement, it has to be able to work forward and backward. But it's usually going to look like this. P, if and only if. If you recall, our biconditional statements, we used a lot of if and only if forms. So if the hypothesis, if and only if, the conclusion. More with those same type of symbols, the negation. The negation is going to be our little squiggly line. I know that it also represents similar, but in this form, when we're talking about conditional statements, it's a representation of the opposite, or the negation. So here we have an example. If our hypothesis was the measure of angle 4 equals 100, then the negation of that hypothesis, remember that means negation, the negation of it would be the measure of angle 4 does not equal 100. If we had angle 4 is obtuse as our conclusion, then angle 4 isn't obtuse would be the negation of Q. So negation means opposite, and you'll notice that this is the opposite of this. Alright, now we have inverse and contrapositives that both use negation, and we have the conclusion and the converse that are not negations but have to do with the order. So the inverse of if P then Q is going to be the negation of P, then the negation of Q. Remember, inverse is just the negation of whatever the original conditional statement was. This is the original conditional statement, so we put the negation sign in front of both the P and the Q, in front of your hypothesis and your conclusion. Following that same example, the converse of P then Q just flips the order around. So the Q and the P switch places with each other, so now it's if Q then P. But it's going from Q to P, it only has one arrow. The contrapositive is going to take this format, the converse, and negate it. So you'll notice that it has the negation of Q, then the negation of P. Deductive reasoning is based on facts, definitions, or properties. Whenever I think of deductive reasoning, I usually think of Sherlock Holmes, and he's asking his friend Dr. Watson to look at the evidence, and he'll look through all the facts of the problem or the case that they're working on, and he'll come up with a conclusion. And then that's usually when Sherlock Holmes would say, brilliant deduction, deductive reasoning. Brilliant deduction, Dr. Watson. Because everything that Dr. Watson was giving him was based on facts, definitions, or properties of the case itself, the facts of the case. So this is not something that's based on observation. This is based on facts we find. Water freezes at 32 degrees Fahrenheit. That's a fact. So if we were to look outside and we were reading that the thermometer was 30 degrees, we're going to assume that any water outside is freezing based on the fact that water freezes at 32 degrees, and we're below that value. Inductive reasoning is more based on the experiments or any observations that you see. So if you were playing basketball and you were observing a player on the other team that you were going to defend, you might realize, oh, they're right-handed because they're always dribbling with their right hand. Maybe you want to force them to their left because that might be their weaker hand. You don't know that that's a fact yet. You're just basing it on the observations that you've seen. So inductive reasoning is different than deductive because this is not based on facts. It's based on experiments or observations. If I flip a coin repeatedly, that's an experiment. If I were to get tails every single time, 5 times in a row, I might say to myself, that's just going to be what I think is the actual answer. That whenever you flip a coin, you get tails. When in fact, that may not be the case. It's more of a 50-50 chance. And a logical argument, if we were in law, we would definitely want to have a logical argument that uses deductive reasoning. Deductive reasoning is based on those facts, definitions, and properties. In geometry, we will use deductive reasoning to present our case for why something might be equal to another, or based on certain given information and facts and properties and definitions, how we could figure out a value somewhere else on the shape. But it's all based on deductive, factual properties and definitions. The law of detachment. Now, we've seen these symbols before. It says if P, then Q. So this is a conditional statement. If that is true, and we know that the hypothesis part is true, then we're going to know that the Q part is true. The conclusion. Detachment means to break something up. So if you were to take a statement and break it up into 2 halves, so if it's raining, then I'll wear a jacket. If we were to just look at the first part and say, well, it is raining, I'm detaching the whole statement. Yes, it is raining, that's true. Then the second part is going to be true. Then I'm going to wear a jacket is going to be true. So the law of detachment takes the statement, breaks it in 2 parts, the hypothesis and the conclusion, and looks at them separately. And if the first part of it is true, then the second part is going to be true. If the first part is false, then the second part is going to be false, according to the law of detachment, breaking it in pieces. And then the law of syllogism. The law of syllogism states that if P, then Q, and if Q, then R are true, if both of those are true, then P to R is also true. In other words, going from here to here. A really good way of saying that is this. If Ben is older than Sam, okay? If Ben is older than Sam, and Sam is older than Lisa, what sort of conclusion can we come to about Ben and Lisa? Well, Ben is older than Sam. Let's say Ben is 20 and Sam is 18. Sam is 18 and Lisa is 16. So how does Ben compare to Lisa? Then Ben is older than Lisa. So the law of syllogism gives 2 if-thens. If Ben is older than Sam, Sam is older than Lisa, therefore Ben is going to be older than Lisa. That's basically the idea that we have right here. So if we were to put this in terms of like the rain and stuff, if it is cold outside, then I'll wear a jacket. If I wear a jacket, then I will stay dry. So if it's cold outside, then I will stay dry. That's how we